All righty. We are recording. All right. So, Gauss law. So we have this idea of an electric field, which is, I mean, in some ways it's, well, everything in math and everything in physics. I mean, really, these are all concepts that we've made up to understand the world around us. But a force is really real. I mean, a force is like a push or a pull. You can put something there and actually measure how hard it's pushing or pulling. An electric field, there's not actually a force there until you put a charged particle in it. Like, I mean, I've got a particle here, okay, it makes an electric field. I guess I'll make it a positive charged particle. But, I mean, that field doesn't really do anything until you actually put another charged particle somewhere in that field. It's like, well, this is not at all right, but I'm going to say it's like carbon monoxide gas or something. They could be filling the room and you never know it until you put a person in there and he faints. But that's a horrible analogy, but something like that. Okay, so we have this idea that, okay, if you have charges in the world, they create these electric fields that go through the world and they do something once you put another charged particle in. As far as what they look like, you kind of tend to picture them like it's fluid flow, even though they're not moving. Because, I mean, if I put a positive particle here or whatever, it'll follow this electric field, right? Or if I put a negative, it'll flow against it. But yeah. So for intuition, it's good to think of them like fluids, and that's kind of what I'm going to do for Gauss law. So the idea of Gauss law, well, there's something in math called flux of a vector field, which basically kind of counts how many field lines go through a surface. So the actual definition is if I've got some surface and I've got some vector field that's kind of flowing through the surface, the flux is, well, it's the field dot area, and that's really shorthand. It's really the vector field dot product with the normal vector of the surface, which I'll tell you what that is in a second, times the area of the surface. So,
by definition, it says through a what?
Through a surface is what that's supposed to say.
Oh, okay. I really thought you said selfie.
We do, what is it, Selfie Sunday or Saturday? What? I don't know. Anyway, okay, so let's do a little flux computation just for the grins of it, and then we'll go back. So, I don't know, let's say if I've got an electric field that's, I don't know, 1,000 newtons per coulomb, and it's going in the I direction. And I've got a square that's in the YZ plane. So if you draw a picture, here's X, here's Y, here's Z. So I've got a square like this, and my field is coming straight through it like that. Okay. If I wanted to know the flux through there, well, I said normal vector. Do y'all know what normal vector means? So normal, well, the idea of being perpendicular is so important in math that for some reason there's 3 different names for it. One is perpendicular, one's orthogonal, one's normal. So they all mean the same thing. But what this normal vector means is if you were standing on the surface, which way would your head be pointed? So if I imagine myself standing on this square, then I'm standing like that. So I'm going in the same direction that the vector field is. All right. Okay. So since it's the same direction, when I do this dot product, remember a dot product is cosine. So theta is angle between vectors. So if I'm standing in the same direction as the normal vector is going, that means my angle's 0. What's cosine of 0? It's everybody's favorite. It's 1, right? So, I mean, that says something really simple. It says, oh, I mean, these lines are actually going through the surface. They're not like skidding off to the side or something. So it's just going to be the force and then times the area of the square is the flux. Right? I didn't actually tell you the area of the square, but whatever it is, it's just whatever that field is and then times the area. On the other hand, if I turn my square around, so let me redraw the picture. Let's say the square is in the, I don't know, XZ plane. So if I draw the picture again, here's my X, here's my Y, here's my Z. My square is setting here like that, but my field is still going in the X direction. Well, now if I'm standing on this square, my head is pointed in the Y direction, right? So what's the angle between my head and these lines? It's 90. So when I do cosine of 90, what do I get? That'd be cosine of 60. Cosine of 90 is 0. So when I do the flux, well, I've got my 1,000 cosine of 90 times the area of the square, which is all 0. And that kind of makes sense because if you think about, I mean, the square is sitting here up on its side. These lines, none of them are actually going through the square. It's like they're all skidding past it. So that's kind of the idea of what this flux is. It's like how much of the lines actually pass through the surface you're going through. All right? Okay. So now that we know what flux is, we can talk about what Gauss' law says. The Gauss' law, well, it starts with a simple idea. It says take a closed surface. Which all closed means, it means that it doesn't have a boundary. So like this square, there's an outside. But like if I do a sphere or something, then, I mean, there is no edge to the sphere. I mean, everywhere you go, you're never going to step off of the thing, right? Okay, and it doesn't have to be a sphere. I mean, it could be like a donut with some holes in it or something. I could have a handle sticking on it. Okay, I'm showing my math side now. But in math, all surfaces, what? Yeah. I don't know. Anyway, math people all think that. Yeah, if you talk to a math person, every closed surface looks like a donut with extra holes and handles put on it. So anyway, yeah, so you take any closed surface. Well, the idea is, well, if you want to count the lines that are going through this closed surface, well, it doesn't matter what my electric field's doing. I mean, it could be going straight lines or it could be going curved lines, whatever it is. You get the idea that, hey, I mean, on one side, all these electric field lines are going to be coming in, but on the other side, they're going to be coming out, right? So I mean, if you kind of Again, it's not really like water flowing, but it's like if you look at a part of the tank and say, okay, how much water is moving through there? Well, a bunch of water is moving in, but the same volume of water is moving out. So if you add it all up, what do you think you get? Like you do what's coming in minus what's going out, you're going to get zero, right? So the flux through this surface should be zero. Why would it not be zero? Well, there's two things. If you go back to like the water analogy, there's two things that could actually throw you off. Let's say, in addition to like your river running through the pipe or whatever, you have a sink that's pouring into there that you're not accounting for. Then you could kind of get more water coming out of the pipe than you see it going in because you don't know that sink's in there, right? Or the sink's in there. The other thing that could happen is there could be a drain where some water is disappearing you don't know about. So you wouldn't see as much water coming out as you see going in because some of it's slipping out this weird drain, right? So, so kind of the caveats, you could have something like a sink that gives you extra coming out because the sink is pouring into it as it's flowing through. Or you could have something like a drain that says there's extra, or you lose something coming out.
Extra coming about?
Coming out. Thank you. You know what I say, what I mean, what I write down, and what y'all hear are like four different things. Okay. Thank you. Oh.
Math major, not English major.
What happened to the screen? I want my screen back. It's weird because there's like still a light there. All right, let's try to get. Does it still say it's connected here? It says it's connected here. Oh. All right, I'm going to go ahead and stop recording while we're waiting for it to reconnect to the thing.